guys, so now we'll be starting off with scalars and vectors. So what is a scalar quantity? A scalar quantity is one which has a magnitude but no direction, whereas a vector quantity is one which has a magnitude and a direction. So we're gonna just quickly go over the list of scalar and vector quantities. So for example, scalar quantities include time, distance, mass, area, density, work, temperature, speed, energy, and power, because we know that these quantities have a magnitude but there is no direction, right? There is no direction of time, there is no direction of mass, there is no direction of area or density or whatever, right? However, when we go through the list of vectors, they include displacement, weight, force, momentum, acceleration, and velocity. And we know that all of these quantities not only have a magnitude but they have a direction as well. So the difference between scalars and vectors is that scalars only have a magnitude and no direction, whereas vector quantities have a magnitude and a direction as well. In this chapter, we'll be going through the addition of vectors, subtraction of vectors, resolution of vectors, the conditions for equilibrium, and how to construct a vector triangle for equilibrium, right? So starting off with the addition of vectors, we'll be using the head to tail concept, right? So what is translation? First of all, we need to know what exactly is translation. Translation refers to picking up an object from one position and placing it to another position while ensuring that the orientation of the object or the vector is not changed. So what we're doing is we're basically picking up the object or the vector from one position and we're placing it on the other position while ensuring that the orientation is not getting changed, right? So what exactly we do in the head to tail method is that we basically pick up the vector and place it on the other position without changing its orientation in order to ensure that the head of one vector is joined to the tail of the other vector, and in this way we are able to basically add the different vectors. For example, here on the screen we have vector A and vector B. So what we are doing here is we'll let vector B at the same position, and then we're going to pick up vector A and we're going to be placing it in a way that the head of vector A is joined to the tail of vector B, right? And in this way we're going to form we're basically going to form a line joining both vector A and B, and this is going to be vector C. And C will be equal to A plus B, right? So C will be equal to A plus B via the head to tail method. What was the head to tail method again? We picked up the vector A and placed it in a way that the head of vector A was joined to the tail of vector B. So in this way, we are able to find the sum of both the vectors, which is vector C, right? So C is equals to A plus B. Similarly, if we place vector B in a way that the head of vector B is joined to the tail of vector A, then again we can find the vector C. The vector C in both the diagrams here have the same direction. So the vector C can be found by either adding A to B or adding B to A. So we'll say that vector addition is cumulative, right? So it is cumulative because even if we are adding A plus B or we are adding B plus A, we're getting the same answer, which is the vector C, right? So in this way we'll find the sum of vectors. So the length will be the same in both the diagrams. As we can see in the first and the second diagram, the length is same and the angle will also be the same. As we can see, angle 1 is equal to angle 2, and the orientation of vector C is same in both the vector triangles. Therefore, we can find that vector addition is cumulative because even if we join the head of vector A with the tail of vector B or the head of vector B with the tail of vector A, we were able to find vector C in which vector C has the same orientation. So this is about vector addition. As we talk about the subtraction of vectors, it is basically the subtraction of vector is basically a sort of the addition of vectors but in the opposite direction. What I mean to say by this is that, for example, here on the screen we have vector A and vector B, right? So basically we know that so here we have got that D is equals to A minus B, right? So what we're gonna do in order to make it from plus B to minus B is that we're gonna basically make the direction of B opposite. For example, initially B was pointing to the right hand side, right? So it was plus B. However, if we change the direction to the opposite side, B is gonna become minus B, right? And in this way we're gonna do the head to tail method again, and a plus minus b will be equal to d, right? So what we're doing here is that we're adding the vectors, however we're changing the direction of one of the vectors in order to get the correct answer, in order to get the correct vector, resultant vector. So in order to change the direction, in order to change the sign of the particular vector, we basically change the direction of the vector, right? So we can see it here as well. We did the same head to tail method. We let a remain at the initial position, initial orientation as it was placed before. In b we made sure that the head of a is pointing towards the tail of b. However, in this case we have basically made the direction of vector b opposite, right? Initially it was pointing to right hand side, now it's pointing to left hand side, and we have used the same head to tail method in order to find the resultant vector d. Similarly over here as well, we've done the same thing. We've used vector a, we've changed the direction of b to make it minus b, then we've used the head to tail method. So a minus b plus a is equals to d, resultant vector d, right? Now moving on to another example is that okay, so first we need to know that the resultant in both of these triangles is the same. The direction of resultant is same, the orientation is same, and the angle would be the same, right? Now moving on to another example is basically we have the vector a, b, c, d and e, right? They're all connected from head to tail. We can see it here as well. They're all connected from head to tail, right? So we know that the resultant would be the sum of a plus b plus c plus d plus e. So this straight line which is pointing from here to here, from the starting point to the finishing point, is your resultant, and we found it by the addition of the vectors a, b, c, d and e by the head to tail method, right? Now we will be doing a question regarding it before we move to the resolution of vector. So the question here basically says that u is the initial velocity, which is 40 meter per second, and it is pointing in it is pointing towards right? And basically v is the final velocity, which is also 40 meter per second, and it is pointing in the direction which is a little upwards from your rightward position, right? So here the magnitude of velocity, the initial and final velocity remain the same. It was initially 40 as well, and final is 40 as well. However, the direction is changing, therefore there is a change in velocity, as velocity is a vector quantity, right? So it not only depends on the magnitude but also on the direction. So since the direction is changing, we know that the velocity is changing. So the change in velocity is basically final velocity minus initial velocity. So v minus u. In order to make u into minus u, we're gonna be changing the direction of u. So initially it is towards the right, now we'll make it towards the left, so it becomes minus u. So v minus u, right? So how are we going to find the direction is that we're going to use the same head to tail method. We're going to make sure that the head of v is pointing towards the tail of minus u, and in that way we're going to be we're going to draw a resultant vector, and that is going to tell us the change in v. Why? Because the resultant is basically v minus u, right? So the resultant vector here is basically going to tell us the change in velocity. So in this way we're going to find the answer. Now we'll move on to the resolution of vectors. So what exactly is the resolution of vectors? It is breaking down of any vector quantity into two perpendicular components. Right, so basically we're going to break down a vector quantity into the two perpendicular components. What are perpendicular components? Two components which would be placed at right angle to each other, right? So these components are generally all horizontal components or vertical components. So basically we break down any vector quantity into two perpendicular components named as horizontal component and vertical component. So perpendicular implies angle is 90 degrees, as I told earlier as well. But before we go deeper into the question, we're going to basically revise a few rules of mathematics, which are cos and sine, right? So what is sine? Sine is basically opposite upon hypotenuse, and cos is basically adjacent upon hypotenuse, right? So in this question, we have a vector which is 5 Newton, and we're going to be resolving it into its two perpendicular components, the horizontal component and the vertical component. So we know that this 5 Newton vector has an angle with the horizontal that is 36.869 degree, right? So when we are resolving it into the horizontal component, we know that cos is equals to adjacent upon hypotenuse, right? So adjacent here is x, which would be unknown initially, and the hypotenuse is 5, right? So we take cos 36.869 is equal to x upon 5, and in this way we're able to find x by basically multiplying 5 by cos of 36.869. so x will be equal to 4 Newton, right? Similarly, when we're finding the vertical component of this vector, we're going to be taking sine. Why? We're going to be taking sine, and what we're going to be doing here is that sine is equals to opposite upon hypotenuse, right? So the opposite would be y, and the hypotenuse would again be 5, right? So we're just going to do the same thing, except that here we're using sine, and then sine 36.869 would be multiplied by 5 in order to find y, the component y, the vertical component, which would be equal to 3 Newton. So in general, what we do here is that in order to for example, if the angle is over here with if the angle is with the horizontal, we find the horizontal component by f cos theta, and we find the vertical component by f sin theta. However, if the angle is with the vertical and not with the horizontal, then we find the vertical by using f cos theta, and we find the horizontal by using f sin theta. So wherever the angle is present, whether with the vertical or with the horizontal, that particular component would be found using cos theta, and the other component would be found using sin theta. So this is what we do here. Now we'll be moving on to a question. So basically we have two vectors here. One is of 6 Newton and one is of 4 Newton. Now in order to find the resultant vector, we know the resultant is basically, since both the vectors are in opposite directions, so in order to find the displacement, we need to subtract these vectors, right? So 4 Newton needs to be subtracted from 6 Newton. So the resultant would be 2 Newton in the direction pointing towards the right. Why? Because forces are vectors. So what we do here is we can introduce a convention of signs. We can say, for example, the one pointing towards right is negative and the one pointing towards left is positive, right? So we write it as force, net force is equals to minus 6 plus 4 is equal to minus 2 Newton. So the minus here is implying that it's pointing towards the right? So this is how we're going to find the resultant vector in this case. Similarly, over here we have a question in which these two vectors are pointing in the opposite directions, upward and downward. So we basically assign them signs. So the upward is going to be, for example, positive, downward is going to be negative, and then we can find the net force by taking upward positive plus 10 plus minus 8 as it's pointing in the downward direction, and so we can find plus 2 Newton. Plus here would imply that the net force is in the upward direction. So this is what we do here. Now here is a little complicated question. It's about the resolution of vectors. So in this question we have to calculate the resultant along with the direction with the horizontal, right? So what we're gonna do, the first step is going to be the resolution of vectors. We have three vectors present here. The vector 1 is 50 Newton, vector 2 is 40 Newton, and vector 3 is basically 80 Newton. So when we're gonna resolve these vectors, we're gonna be resolving them in both horizontal and vertical directions, right? So the horizontal component of 50 Newton is going to be 50 cos 30, and the vertical component is going to be 50 sin 30. Similarly, for the 40 Newton vector, the horizontal component is going to be 40 cos 20, and the vertical component is going to be 40 sin 20, and the 80 Newton vector is going to be resolved into horizontally it would be 80 cos 15, and vertically it's going to be 80 sin 15. So in this way we're going to have the resolved vectors in all the four different directions. Now the next thing that we do here is that for the horizontal direction, basically we're going to give them a sign, right? For example, for the horizontal direction, we can say that towards the right it is positive and towards the left it is negative. So first we're going to solve for the horizontal direction, right? So when we're doing this, the net force will be positive minus positive. We're going to be basically adding all of these forces, but obviously if the sign is different, then that particular force is going to get subtracted, right? So towards the right we have 50 cos 30 plus 40 cos 20. However, towards the left we have 80 cos 15. So we're going to be taking it as minus 80 cos 15. So even though we are adding it, but obviously since its sign is negative, so it's going to be ultimately subtracted from this, and the net force is going to be 3.6 Newton in the horizontal direction, right? When we're basically going to be solving it for the vertical direction, we're again going to give it the sign. We're going to basically say that for example, if we give positive to the upward direction and negative to the downward direction, so we can find the net force by basically 80 plus 80 sine 15 plus 50 sine 30, because both of them were in the upward direction, and then we'll add it with minus 40 sine 20. Why are we taking it as minus? Because it is in the downward direction, so it's going to be ultimately subtracted, and in this way we're going to find the net force, which is 32 Newton, right? So in this way we have found the resultant forces in both the horizontal and the vertical direction, right? However, the question said calculate the resultant along with the direction with the horizontal, right? So what we're gonna do is that now that we have both the net forces in the horizontal and the vertical direction, we're gonna basically be finding the resultant by finding the root of the squares of both of these forces. So 32 square plus 3.6 square, and then we find the square root of this, and that is going to be 32.2 Newton. So in this way we're going to find this. Why did we use this method? It's because we know that hypotenuse square is equals to perpendicular square plus base square. So obviously if we rearrange that, it's gonna be the root of the squares of both perpendicular and base. So we know that the perpendicular is 32 Newton here, the base is 3.6 Newton here. So we'll find the squares of both, we'll add that, and then we're gonna find the root in order to find the hypotenuse, which is gonna be 32.2 Newton over here. So here we found the resultant. However, we also need to find the direction, right? So what we're gonna do for the direction is that we know that tan is basically equal to opposite upon adjacent, right? So here we have basically the angle here. We need to find the angle. So what we're gonna do is we're gonna take tan of the angle and we're gonna divide 32, which is basically your opposite, by your adjacent, which is 3.6, right? And then we're gonna take tan inverse, and in this way we're gonna find the angle. So we basically know the resultant along with the direction with the horizontal as well. With this we'll be moving on to equilibrium. So basically what is equilibrium? If the resultant of all the horizontal forces and the vertical forces turns out to be zero, the object is said to be in a state of equilibrium, right? So this is the first condition for equilibrium. What? The resultant of all the horizontal forces and the vertical forces works out to be zero. The object is said to be in a state of equilibrium. So basically this is the condition for equilibrium. Now we'll move on to the steps which are used to construct a vector triangle for equilibrium. So the first step is that we need to make sure that each side of the triangle represents one of the three forces. So since there are going to be three sides, so it's going to represent three forces, right? So each side is going to represent one of the three forces. The second step is that the length of each side corresponds to the magnitude of each force. For example, if there are three forces and one of them is larger, then obviously the length of that particular side is going to be longer as well, because it is corresponding to the magnitude of the force, right? Now the third step is that the three forces are joined together such that all arrows point in the same direction. So all of them would be joined from head to tail in a way that all of them would be pointing in the same direction, right? So it's going to be continuous. Now the fourth one is that this kind of a vector triangle is called a closed triangle. So this is basically called a closed triangle, and if a closed triangle is formed, equilibrium is established. So if we form a closed triangle, it is an indication of equilibrium, right? So now we'll be doing a question about it. So here it says that the photo frame is hung from the wall, and so we can see it over here. So obviously since it's hanging on a wall, so we know that it's in the state of equilibrium, right? So first of all, there is an important point to note. It is that the direction of tension is always away from the concerned object. So for example, if the object is pointing to downwards, then the direction of the tension will always be away from it, so it's going to be upward, right? So in this question, the first part is to find T by the resolution of forces. So for the resolution of forces, all vectors shall originate from a single point, right? So in order to make sure that all the vectors originate from a single point, we need to arrange all forces in that manner. So over here we can see that we can take the first tension as the first force and the second as second, and the we can take the weight as basically your third force, right? So we're gonna make sure that all forces are arranged in a manner that all the vectors are originating from the single point. So here we have taken this as the single point, and then we're gonna make sure that all of these forces are emerging from the single point only. So weight is obviously acting downward, so it's 60 Newton, which is pointing in the downward direction, and we know that the tension is always direction of tension is always away from the concerned object, so it's gonna be towards the upward direction. Now what we'll do here is that we're gonna be solving this in the vertical direction. So obviously, since we already know that it's a photo frame that's hung, we know that it is at equilibrium, and at equilibrium we already studied that the condition was that the net force was equal to 0, right? So first of all, we're gonna be giving them signs. So in the upward direction we can say that the sign is positive, and in the downward direction it would be negative. Right, so when we're basically solving this, we're gonna be taking the components, the vertical components of both the tensions, and we're not gonna be taking any component of the 60 Newton force. Why? Because it is not an at angle, it is basically 0 degree to the vertical, right? So we're not gonna be taking its component, so we're just gonna take it as it is. However, since it is in the downward direction and we already assigned the minus sign to the downward direction, so it's gonna become minus 60. So while finding the net force, we're gonna write it as T sine 70, which is the vertical component of the tension, and then we take add it with T sine 70 again, which is the vertical component of the other tension, and then we add it with minus 60. Why is it minus? Because it's in the downward direction, and we equate it to 0. Why is it equal to 0? Because the net force would be equal to 0 because it is in equilibrium, right? So in this way we solve it, and we're able to find that basically your tension is equal to 31.9 Newton. Last thing from this topic that we'll be going through is the resolution of forces on an inclined surface. So here we can see there is a box which is placed on a slope. So in order to resolve the weight of the force in the two directions, the vertical and the horizontal directions, we need to basically resolve both of these vectors, right? So what we're gonna do, it says resolve weight such that one component is parallel with the inclined plane and the other is perpendicular to the plane. So here we form the two components. This one is parallel to the inclined plane, this one is perpendicular to the inclined plane, and in this way what we basically do here is that we know that we have an angle here and we got this angle here. So what we're gonna do is that we know that the vertical component is gonna be mg cos theta, right? So the component of weight which is acting perpendicular to the inclined surface is going to be mg cos theta, and the one which is acting parallel to the inclined surface is going to be mg sin theta. So in this way we're going to resolve weight in its two perpendicular components. With this, we've completed the first unit, which is physical quantities and units. Stay tuned for the upcoming videos. Bye bye.